okay. We can put another microphone. Well, and now down your t-shirt. Okay, right. Okay. Is it comfortable?
Yeah, that's okay.
Okay, you have a mute. You have a mute, so we have to.
Okay, while our
So
speaker
here,
gets
okay,
comfortable,
like this.
All right.
let me present the next talk. So the next talk is ProtogaLattice. I guess it's a word game. And David Balbas will be giving the talk. So the floor is yours.
Okay, just let me try if this works. Yes. All right. Well, hello. Thank you very much, Carla, for the introduction. Can you all hear me well? Because it sounds a bit weird when you're on stage. Okay, good. So I'm David Balbas. I'm from coming from ETH. I was at IMDEA until 4 days ago. So technically, I did this work while at IMDEA and also while at Input-Output. And this joint work with Ankani Tudescu, who's just over here, and Maxime Plançon, who couldn't come to ZKProof. And we're going to present ProtogaLattice as a new constant round lattice-based folding scheme for general polynomial relations. So we just talked about folding schemes, so I will not make the introduction of folding schemes very long. Just to introduce some notation, which is kind of similar to what Michal was presenting. A folding scheme is essentially a reduction of knowledge. It's not a snark. It's not a full snark. Okay, it's just a reduction. So what do we have? We have a base relation. That is the relation we have here on the left. We can have one instance of this base relation. We can have k instances, which is our case. We just denote this by multifolding, and we're dealing with multiple instances. And then we have a special relation, which is the accumulator. The accumulator goes over and over throughout multiple rounds of folding. So taking a base relation and an accumulator, we can put them all together into a new accumulator. Essentially, the base relation has an instance, which is known to both the verifier and the prover, and a witness, which is only known to the prover. And an instance is generally going to be a commitment to the witness, an homomorphic commitment. And the process really looks like follows. The prover and the verifier take these instances and these witnesses, put them together with the accumulator, they throw them into the folding protocol, and they end up with a fresh instance and witness of the accumulator and the proof. And I see that, well, the slide is a bit off. I hope it's only here. To introduce also some notation, the relation that we're dealing with, the base relation, is going to be parameterized by a function f. This function f represents your favorite structure. It can be R1CS. In this case, it's going to be a degree 2 function. It can be CCS for where it is a polynomial function. But essentially, it's something that applied on the witness, it is 0. And then we also add to this relation the fact that the instance is a commitment of the witness. We just express it like this for convenience, to be more general. So what relations can we fold? Essentially, as I just said, this is determined by this function f. We have, in the case of Nova, that was the first folding scheme, f is 1. R1CS is a degree 2 polynomial that is structured. There are also some check-based folding schemes like ANOVA, lattice fold, cyclo. They allow one to fold more expressive relations, in this case, structured degree D polynomial functions. And there's even a more general kind of folding, which is introduced by Protostar and Protogalaxy, which folds transcripts of special sound protocols. I don't want to get into the details of what this arithmetization is exactly, but just to make it clear, it includes all the other types of arithmetizations that we're used to, such as CCS, is natively compatible with Plonkish. It can fold also some kinds of lookups, etc. So it's like, let's say, the most complete of all of this. And here, f is just an arbitrary polynomial function. It doesn't even have to be structured like CCS is. So, okay. So in lattice-based folding, when it comes to folding expressive relations, like at least CCS degree D, we have essentially 3 works, and the previous related works like Neo and Lattice Fold. These are Super Neo, Lattice Fold, and Cyclo, all of them very recent. And they are all very similar in some ways. They all fold the CCS relation. They all borrow techniques from Hypernova, in concrete, the sum check of Hypernova. They have different range proofs, different proof sizes, and they also, all of them have a lot of rounds. I think someone, I don't know if it was Christian, mentioned before, having a small number of rounds in folding, sometimes it's important because it allows us to reduce the verifier circuit size, because we have to encode the random oracle calls. And since we're doing incrementally verifiable computation, we have to prove these random oracle calls. So it's good to have less random oracle calls than 30 in general. And this is essentially why we decided to work on a new protocol, a new folding scheme from lattices that we called ProtogaLattice. It's a new approach. It kind of diverges from the sum check-based approaches that the other works have been introducing. It's versatile in the sense that it folds arbitrary polynomial relations, as the previous Protostar and Protogalaxy. It is multi-folding friendly in the sense that we can take multiple instances of the base relation and fold them all together. It is constant round, which is positive, as I just said, because the overhead in the IVC verifier circuit is much smaller. And this is because we're avoiding sum check. So we really have to depart from the sum check-based techniques that these previous folding schemes were using. And we don't have an implementation. We only have some parameter computation. But I would say we have a competitive proof size, and we have no reason to believe that this should not be efficient when deployed in practice. OK, so putting it in the table together with the other schemes, it looks like that. We're folding a different relation, arbitrary polynomials, a bit more general. We're using a different techniques, which is multivariate polynomial interpolation, and a bit of heavy multivariate polynomial machinery, as you will see. Our range proof is black box. This means we're not introducing any new range proof, but any range proof that you want works in our protocol, as long as it satisfies the constraints for our function. And the number of rounds is 4 plus whatever the range proof is going to introduce. And the proof size is also sort of competitive with the other schemes. OK, yeah, my slides are moved. I don't know why. I hope this is not a big problem. But well, essentially, let's start with ProtoGalaxy, which is the starting point of our work. So for a polynomial map, f of fm to f, we're taking size of witness as m, only one output for simplicity. The base relation is expressed as we had before, characterized with this function f that evaluated on the witness is 0. This characterizes what a valid witness is. And the accumulator of ProtoGalaxy introduces an error term into the base relation. So an accumulator doesn't have to satisfy that f of w equals 0. It's enough to satisfy that f of w star, in this case, as it's an accumulator, equals this error term e, which is part of the instance, and it's also known to the verifier. And as I just said, in reality, we're considered, yeah, I would really like to somehow change my slides, because I think if this is moved all the time, let me just see. Oh. Is there any chance I can plug in my computer? Maybe. Excuse me. Is there any chance I can plug in my computer? Yeah. OK. So I'm sorry for this. But I don't know why this happened. Let's see. Because yes, I'm just connecting to Wi-Fi. Okay. Okay. Yes. And this will not work, of course, but I can pass it with my computer. Okay, sorry about that. This is much better. Now my monitor doesn't work, so I have to turn back because it's flickering. Okay, so let me just recap. We're talking about Protogalaxy, which is our starting point. Protogalaxy is a classic folding scheme, not based on lattices. We have polynomial maps, and we have the base relation that we just mentioned. And we have an accumulator that introduces an additional error term into the relation. Okay, so this is a simplification. In reality, our function is going to have multiple rows. So it's fm to fn. And we also have to randomize all of these rows. But since we're not really doing any change on this aspect with respect to Protogalaxy, we're kind of avoiding this complication just for clarity. And in Protogalaxy, the folding works as follows. So the first step, the prover has to combine the witnesses, W1, WK, and the accumulator into a polynomial that interpolates all of them. So we're really creating sort of a quantum superposition of all the witnesses and the accumulator we have by putting them all together in a polynomial. Okay? The second step is the prover is going to compute the new error function evaluated on the polynomial with the witnesses. This is done by simply evaluating f on the polynomial that we just made. And the third point comes when the verifier samples a challenge, and then the prover will evaluate the polynomial on this challenge. This will determine the new accumulator, and will evaluate also the error function on the challenge sent by the verifier, and this is going to determine the new error. This is the way where we create the next accumulator. It's a very simple protocol. The verifier sends this one challenge, and it determines everything that the prover has to do. Now, as I presented, this is not sound yet, although I haven't really gotten into the math. But for this to be sound, we need a connection between the error of the previous accumulator and the error of the accumulator that we obtain. Otherwise, the prover could just come up with whatever error they want to claim and make this protocol work for any witnesses, not necessarily part of the base relation. So we're missing this link. And for achieving this link, we actually need a little bit of math and a very neat trick that I will present next. So Protogalaxy interpolates witnesses and accumulator using Lagrange polynomials. Lagrange polynomials are something that we're all very familiar with. We selected domain H, sometimes the roots of unity for faster software. We choose the vanishing polynomial over this set as the product of all the elements on this set H. And we have a very neat lemma, which essentially says that when we evaluate our polynomial map on the linear combination of the witnesses factored by these Lagrange polynomials, the function f, the polynomial map, behaves linearly, modulo the vanishing polynomial. So I'll let you stare at it for a couple of seconds. We really can take f, take the Lagrange polynomials outside of the sum, and put it on the right side, evaluating only the witnesses. And if you've been following me, every witness that is coming from a base relation satisfies that f of wi is 0, because it is a valid witness. So if we consider this sum and we consider that these vectors are actually valid witnesses, the sum on the right is going to be 0. But not for the accumulator, because the accumulator is not a valid witness. So the accumulator is exactly going to be E, f of w star. And this is the trick that Protogalaxy uses to connect the previous error of the accumulator and the new error of the accumulator. So it works as follows. The prover computes the interpolation of the witnesses, this interpolation polynomial. it computes the error function. It already uses the lemma to compute the quotient polynomial, modulo c of x, plus the offset. And it sends the quotient polynomial only to the verifier, instead of sending the whole error polynomial. And this is the part that gives us soundness. The verifier just replies with the challenge, and the prover can update with exactly the value that should correspond in case all the witnesses were honest. And the verifier can do the same on its side with the instances. This is with the commitments to the witness instead of with the actual witnesses. And this, with a bit of careful analysis, gives us a sound protocol. I hope you just, as a takeaway, the main idea is we need this linearity lemma and this trick, which is very neat, to connect the errors from the previous accumulator and the new accumulator. Great, so now can we just throw in lattices and make this work? Not quite. Let's start by having a few attempts. The first thing that comes to mind is we have some possibly better sign commitments or homomorphic classic commitments. Let's throw in I-type commitments. So we have a public matrix A. We compute our commitments in the useful way, and we need that our witnesses now are bounded in order for the commitment to be binding. So we need them to be less than a given norm. But then, if you remember how we were interpolating instances and witnesses using these Lagrange polynomials, we get that the accumulator gets an expression like this. And the L0, Li coefficients evaluated on a challenge, they get very big. So this means that we're losing binding on the accumulator, on the new commitment that we get on the accumulator. So this is not the right way to go. One solution is to use a small challenge set, okay? If we take C to be of a small challenge set, say polynomials with entries -1, 0, 1, 2, this actually gets much better. We control the noise a little bit better, and it can work. It can work to control the norm in this way, but as soon as we go for k larger than 1, this also, because the polynomials start being of higher degree, this also just creates too much of a norm expansion to be a bit of a non-controllable thing. So yeah, this is a good solution if we just want to fold one witness, and we could actually stop here, but we were a bit more ambitious, so we wanted to continue folding. And for folding k larger than 1, we rely on multivariate polynomials. So let's see how we do this. The first idea is to build an accumulator recursively. The case for k equals 1 works. So why don't we start from there? Okay? If we want to fold k, we can just take 1 by 1 and build an accumulator iteratively. So we have that the accumulator on the jth step is x times the accumulator on the j-1 step plus 1 minus x times the new witness that we're doing. And x and 1 minus x are exactly the Lagrange polynomials for k equals 1. So this works, okay? But with this, we cannot really do folding in one round as we wanted. We will have to have one round for each of these witnesses that are coming and create a very long transcript. So we need something a bit better, but we have a very nice change of variables that actually allows us to relate the expression corresponding to the final accumulator to the original accumulator and the original base witnesses. Here with mathcal y, I'm just representing y0 all the way to yk, so all the y variables. And this expression is going to be our new accumulator in the multivariate setting. All right, so actually if you look at this, here you can see that if we plug in a small challenge, the norm is not that big. We don't have anymore any polynomials in the factors, so we're really reducing the norm expansion by using a closed expression like that. So can we sample just a set of k plus 1 small challenges from a challenge set and fold everything at once? I wouldn't be here otherwise. So yes, this works. It works with some additional considerations. In particular, we need to attach a range proof for each of the instances, for each of the commitments, and we need to find an equivalent linearity lemma for soundness. We no longer have Lagrange polynomials, So we have to work our way in order to get a linearity lemma. And luckily enough, and I will not get very deep into the math, we can have a lemma that is equivalent over ideals. So this lemma says that the function f actually still behaves as linear modulo an ideal I that has a basis like this. Complicated math, but what matters is that we can actually use, the prover can actually use the pre-computed reduced Grosvenor basis of this ideal and compute a Euclidean division that turns out being nice, fast, and exact. So it's really, we managed to get an equivalent to the previous lemma with multivariate polynomials. Okay, great. Now I want to scare you. This is how Protogalaxy, original Protogalaxy, non-lattice-based looks. This is how our protocol looks. You can see there are a few more rounds of interaction. Here there are in total 3 full rounds. This is because of randomizing the coefficients that I said I wouldn't talk about. But what I want to convince you here is that it's not that much complicated than the original Protogalaxy, which is actually a very efficient and implementable protocol. So yeah, it's not that scary. That's the takeaway. Okay, so there's one caveat on everything that I've been telling you so far, which is that we have this accumulator and we sample small challenges, but still we have some norm growth on the accumulator. We managed to control it. We've managed to have it very low, but by only having the y0 factor and the subtractions of the challenges. But there is still some growth. So if you look at the diagram on the right, we are going from an accumulator that is bounded by b to an accumulator that is bounded by b prime, where b prime is larger than b. So we need a way, if we want to build IVC and continue folding, we need a way to control this and to bring our protocol, our accumulator, back to the original norm. So for this, we introduce a second protocol that is run after folding, which we call bootstrapping, because the only run it does is taking an accumulator and reducing the norm of this accumulator. So the bootstrapping protocol that we introduced really takes W prime star, an accumulator that we got from folding, passes it through some shadow folding scheme that we come up with, and gives you a proof and an accumulator with a stronger bound. How do we do this? I don't want to get into the technical details also for the sake of time, but to give you an idea, it's not as easy as how this is done, for example, for Cyclo or for lattice fold and so on. And the reason is that we don't have linear relations. So in some check-based folding, for those of you who are familiar with these schemes, what people normally do is they decompose the witness in some basis, and then since the relation that you have after the sum check, the accumulator relation is a linear relation, you can just send commitments and error terms to the verifier, and everything behaves linearly, and it's very easy to check on the verifier side, roughly, okay? But our problem is that our accumulator relation is not linear. It's highly nonlinear because it uses the same polynomial function that defines the base relation. And this is normally degree 5, 4, 5, 6, or whatever. So we have to work a little bit harder. And what we do is introducing some protocol that does some sort of shadow folding of decomposed accumulators. Unfortunately, I don't have time for the technique. I'm very happy to discuss it with you. And I also think this protocol is sort of independent interest. I don't know exactly in which situation this could be useful for another protocol, but we're taking an accumulator and reducing its norm. So it really sounds a bit like FHE bootstrapping, and it works for any relation. So if at some point you have a folding scheme that you don't know how to control the norm of, maybe this is useful for you. Could be. I don't know. And this protocol is only introducing one more round of interaction to the protocol. Okay, so I'm already wrapping up. There are quite a few open questions. This is still pretty much a work in progress, and since it's kind of a very new approach, we're still facing some difficulties. One of them is whether we can bootstrap as little as possible, because the bootstrapping is a bit more expensive than the folding. So it's good if we can avoid doing it so regularly. And for this, Cyclo, which Michal just presented, does a very nice trick, which is in the accumulator, that is the amount that is growing after every folding, is growing multiplicatively. We can try to plug in a coefficient 1 so that the norm doesn't grow. It grows only with the base witnesses. And I think this trick, we kind of analyzed it. It seems to work, but we need to plug in an extra variable, which makes our folding a bit more expensive. So we're welcome to hearing ideas on how we could do this without this extra cost. Also, there is a major open problem, I would say the main, which is designing a range proof that is suitable to this protocol in the sense of maintaining round complexity. This is a constant round range proof that behaves well with ProtogaLattice. We're also looking at options, but nothing has been, we haven't really come up with a full range proof yet. So we're also very happy to hear your input on this. And also, of course, perhaps implementing the scheme and actually finding how competitive it is in practice. And yes, ideas are very welcome. So this is my final slide. As a summary, we are introducing a new lattice-based multifolding scheme for general relations, general polynomial relations. It's constant round. We use multivariate polynomials. We present a bootstrapping protocol that reduces the norm of an accumulator of any relation. And we still have quite a few open questions, and it's pretty much still a work in progress. I also have some parameters for a typical degree 5 relation, witness size 2 to 25, and without counting the range proof. As you can see, our proofs are more or less in line with Lattice Fold Plus and Neo. And efficiency-wise, we also have no reason to believe that it shouldn't be slower, modulo having a suitable arithmetization as well over rings. And yeah, thank you very much for your attention. I'm happy to take questions.
Thank you, David. Any question from the audience? The camera is not a hand.
Patrick?
Thank you. It's a question / remark, is that the thing which reduces the norm of the accumulator is extremely powerful, because you don't just reduce the norm of the accumulator, right? You have to maintain soundness, which means that the new accumulator should guarantee that, you know, every witness that you accumulated will also find. Mm-hmm. And that seems like really, really powerful. So if you could just like give a 30 seconds, summary of the idea.
I can give you a 30-second overview. I'm going to give it in the univariate polynomial case, because it's more intuitive. So the idea is to decompose the witness in base B first, and then to fold these bit decomposed witnesses on their own using the Lagrange basis, but in such a way that you can find some point in which the evaluations of the Lagrange polynomials correspond exactly to the base in which you're decomposing. So L1 would evaluate to B, L2 would evaluate to B squared, and so on. This is not the challenge point of the verifier, but it is a point that we can use to check that the decomposition has been done correctly. And Lagrange polynomials have to add to 1 when they are evaluated. This is a requirement. So for this, we need to add a shadow witness, because otherwise we don't have enough freedom. That's the rough idea. And then translating this again to the multivariate case.
Yeah, I mean, for me, it was more like how you managed to reduce the size. But my problem was like how you managed to reduce the size but still maintain that. That's
Yeah. So these witnesses you're folding are the result of decomposing the original witness, which has a larger norm. And then you decompose them, you kind of fold them, and when you aggregate them, the norm you get is lower again. And you have the same relation. You have the same accumulator relation.
Any more questions? I think
over there, there's a question.
I was just curious, you were talking about the range proofs and whether they increase the number of rounds, but I guess often you use folding schemes, so like you do many folds in a row, right? Mm-hmm. So you can't you sort of like does the round complexity of the range proof matter? I guess some point you're sort of like committed to these are kind of the things you want to have in a certain range, and then you just, you know, I mean, if at some point later in round number 3 of folding you suddenly detect, hey, there was a problem in round 1, wouldn't just go back and say at that point, well.
It is true, but here we have to really send the range proof. And if there is some interaction happening, it's going to be, again, embedded into the verifier circuit. So it's going to increase the number of rounds.
I see what you're saying. Okay,
and it's really like something we can put at the end of the proof. So yes.
One last question. Do you have like, do you have any numbers of the verifier circuit of like how would we? No. Okay.
No, because we didn't implement, and we're only 3. We welcome people.
Okay. I think we're running out of time, so if there are no more questions, we will move to the next talk. Michal, you again.
Okay. Now I have to.